Let's have a quick high-level overview of how the storage looks like. So you have this circular disk called the platter, and it has multiple concentric circles within it, forming a track individually, like a racetrack. This platter is also divided in the form of pizza slices, where each slice is called a sector. And the intersection between a sector and the track forms a block, which I've shaded in red. And the block is the most fundamental unit of reading and writing to and from the disk. So if you're interested in a very specific byte, which is in this block, you won't be reading just that solitary byte. What you will be doing is reading the whole block, storing it in RAM, working upon it, and writing that block back into the storage. So why do we do this? Why don't we just extract a single byte? And a major reasoning for that has to do with the principle of locality of reference. So what this means is if you are operating upon byte B10, there's a very high likelihood that you won't just stop there. You will be accessing memory close to it as well. You will be accessing byte B9, you'll be accessing byte B11. So taking the example of a Java program, if the execution engine executes one line of code, the next line is literally right next in the address space, unless it has to jump across functions. In that case, it'll have to jump across different address spaces. But for most scenarios, there's a very high likelihood that if you access address 1, you will also be accessing addresses near to it. That is the principle of locality of reference. So we have this motorized arm called the spindle, which physically moves across a track, goes to the specific block that we want, and retrieves it. So let's say you are running your Java program and you're currently in some function and you're dealing with this block in red, and you make another function call. It'll obviously be in some other address space. Let's say it's in some other block on the other side. Your program's pretty big. So in that case, the spindle will actually have to move all the way across the sectors, grab that block and store it in the RAM. So because the spindle is a motorized arm, it actually moves. Your seek times, your write times will obviously be pretty slow when you deal with a disk as compared to volatile memory like RAM. So over here is the average access time for a disk versus a RAM. Disk access will be in the order of milliseconds, and RAM access will be in the order of nanoseconds. So for the purpose of this video, assume that you're going to create your own database software. So we'll start off with a very crude implementation and talk about different trade-offs, different approaches, different design principles, and come up to a conclusion towards the end of this video. So let's start off with a very crude implementation. Your database will just function like a text file. So every new record that you write will be appended towards the end. So you write one record, it'll be here, the next record will be right next to it, so on and so forth. So obviously, this is pretty quick in terms of writes. So you don't have to write in a specific order. Writes will take constant time. Where it falls short is in seeks, in searches. So if you want to search for a specific record, because you're just inserting it sequentially without any sort order or anything like that, you'll have to do a complete linear scan. And because we're doing a linear scan, it is asymptotically equivalent to an order n time complexity. Now let's say your database file is pretty big, so it won't necessarily fit in one block. So in that case, you can have multiple pages. A page is for most purposes equal to a block size. So your database file can span across blocks. So it might not be the case that one block will be right next to the other block in terms of your database file. It could be in some totally different location wherever there's a free block. So if you read the last entry of block 1 and you want to read the first entry of the next block, then your arm has to physically move to that location wherever it is and grab that block. So this won't scale well because of this linear time complexity, and this is what indexes help achieve. Indexes, their primary goal is to help optimize reads and also writes to some extent. So you'll find that with all the indexing approaches that we discuss, your reads will nowhere touch linear time complexity. They'll be at max logarithmic n. Even your writes, the amortized time complexity won't be linear. It'll still be way more efficient, but the focus is on optimizing the read complexity. So going back to your custom database application, your main goal is to service read requests which come in at scale, and to service them pretty efficiently, you want to do better than linear time complexity. And a secondary goal is also servicing write requests in an efficient way as well. You don't want it to be anywhere near linear time complexity. So you decide that your database application will make use of indexing techniques, and you start considering the hash indexing approach. So what hash indexing entails is you have this hash map which resides in memory. The hash map, if you're aware, will take in some input. It'll hash out the bucket for the hash map, and in that bucket you will map out your value. So let's say you want to write a record and the primary key for that record is ABC. You will hash out ABC and you'll get some hash code value, and this value will serve as the bucket number in the hash map, and to that bucket number you will plug in your entire record. So there can be multiple approaches for this. One of them is in this bucket having the entire record which resides in memory. Another approach is just saving the record on the disk and having a pointer to that disk over here as the value. Let's go with the first approach for our database for simplicity. So we have the primary key, we hash it, we get 1, and in 1 we store the entire record as a node. So there can be cases where you have collisions. So let's say you have another record coming in with some other primary key and you hash it, and it's also assigned bucket 1, but you already have a node at bucket 1. So in that case, you look at some collision resolution methods. One of them is chaining. So you basically maintain a linked list as the values in the hash map. So if you have 1, you already have a node over here. The node will contain 2 properties. One is obviously the record, the entire value of the record, and the second property is pointed to the next node. Another method is linear probing. So instead of just hashing the primary key or any other key of your choosing, you will plug in some linear constant along with it. So let's say you hash ABC plus 1, you find there's already something in bucket 1, then you'll sequentially increase your linear constant. You'll then check what the hash of k plus 2 will give you, and so on and so forth. If you still find that you have collisions depending on your data set, you will then maybe consider quadratic probing as well. So instead of just hashing the key, you will add in some quadratic function to it. Let's say h of k plus 1 square. If that is also filled, you'll choose h of k plus 2 square and check if that's empty, so on and so forth. So reads over here are pretty straightforward to implement. Let's say you get a primary key, you will hash that key, you'll get a bucket, you go to that bucket, see if the record exists and return that record. If that record is not, if that record value has a different primary key, it means that record had a collision and it's in some other bucket. So then you'll do linear chaining, you'll do linear probing, quadratic probing, whatever mechanism you chose for collision resolution, and fetch that record. The average time complexity for that is going to be constant time. Writes over here are also pretty trivial. You get in a new write record, you'll hash the primary key, you get the bucket, and you just plug it in that spot. So reads and writes both are constant time. So this is a done case, right? We can just end the video over here. This is way better than linear time complexity. But hash indexing has its own drawbacks, and we'll look at it in a while. So you start thinking about your approach and you start probing if there's any possible drawbacks for this. And there's one glaring drawback. Because this entire structure resides in memory, let's say you have some fault in your system, there's some interruption and your system shuts down. And when it boots back up, your entire data is lost because it's in memory and memory is volatile. So your entire source of truth for your data is just this hash map which contains the key and the value. So what we'd ideally need is some sort of backup of this data on the disk. So you decide to go with this sort of a structure. So let's say you get a new write. Let's say it's to write a new record where the primary key is ABC. So your system, your database takes in that write, tries to enter it into the database, and let's say the write is a success. Then you'll update the hash map and send a success message to the user. The commit was successful. But you start thinking a bit, and then you notice one really big downside to this approach. Let's say you have a query which tries to update multiple records. Say, update all records with the age is 10. This can affect multiple records. And you make changes to ABC, DEF, GHI. And as you're making changes to PQR, the system shuts down. There's a failure. Now, when the system is back up and when you look at your database state, it's in a corrupted state. You have partial data written. And now there's no way to roll back or undo the change that you've made because you've not stored the operation that you've made anywhere. So while we didn't necessarily send a commit successful message to the user, you still ended up writing partial data and corrupted the database. What would be more helpful is storing or having a log of all the operations that we are doing, and that makes it more easier to roll back if needed. So this brings us to what a write-ahead log is. So for persistence, you decide to introduce this middle layer called the write-ahead log, which is basically a log file stored on the disk. So let's see how your custom database application will service read, write, and update requests. So read requests are pretty trivial. It will go to the in-memory hash map, and your hash map already has the record stored along with the hash key, and you can instantly fetch that record. What about write requests? So your application will receive a write request, let's say for record DEF. And the first thing that you're going to do is open the file containing the write-ahead log. So if you're writing a C program to implement your database application, you'll have to make use of the open function to open the file using the file descriptor containing the write-ahead log. You will then make note of the operation that you're doing, which is writing for record DEF. And once you're able to save it onto the disk, you will then send a commit successful message to the user. So notice how when the request came, we just wrote it, made sure it's written into the write-ahead log, and only then sent a commit success message to the user. We did not bother sending it to the database. Why is that? Because our data is already in two places. First is the volatile memory to service requests, and it's also persisted in the disk with the help of this write-ahead log. We already have a backup of it. So let's not worry about the database, storing it into the database for now. So when do we push things into the DB? So your write-ahead log will have 10, 20, 30 entries, and it'll maintain a buffer of them. And periodically, you can spawn a new thread for your database application. And that thread will basically, again, read from the write-ahead log and also open the file containing your database and push whatever new entries are there from the write-ahead log into the database. So it batches entries. As a side note, when you add in an operation, maintain a log in the write-ahead log for your operation. With the note of the operation, you'll also add in a checksum. So let's say your operation is insert for ABC and some data. You will also add in a checksum with that entry, which is nothing but a hash of whatever you wrote. This is for data integrity. Why do we use this? One application is for the issue that we discussed that brought us to a write-ahead log. So let's say that you get a write request that requires making changes to 10 records, and you make note of that operation in the write-ahead log that you need to make updates to records with keys A, B, C, D, E, F, so on and so forth. And before you complete making note of that on the write-ahead log, your system shuts down. So you've partially written the operation on the write-ahead log. Now, when your system comes back up, you open the write-ahead log and you see what the last entry was, what the last transaction was. And you see that it's partially written, the checksum is not there, or the checksum is incorrect, and you decide to just scrap that entry. Either ways, you never sent a commit message to the user, a commit successful message to the user. So there's no point keeping this log on the write-ahead log. So you can just scrap this entry and pretend that it never existed to begin with. So rolling back of transactions is pretty easy. So in this way, we can ensure the integrity of our database and also guarantee atomicity of all transactions with the help of a write-ahead log. Also, when our system comes back up, yes, you have the write-ahead log in its integral form with all committed entries, but your hash map will be destroyed. It's volatile memory. It'll be a clean slate. So how do you reconstruct this hash map? It's pretty easy to reconstruct because you already have a backup in the form of the write-ahead log. So you will go over the operations one after the other in a sequence and reconstruct your hash table. So the key takeaway from all of this is if you want persistence, it makes sense having a write-ahead log. So we saw servicing read requests, write requests. What about update requests? What if we've already written ABC, DEF, GHI, PQR, and now we have to update ABC? Do we move the spindle all the way to ABC and overwrite this content? No. What we instead do is a more efficient approach. It's to just make a new version of ABC and append it towards the very end. So your write-ahead log will have OPABC, OPDEF, and all the other operations. And towards the very end, if we get another update, we just add that update as if it were a write. So OPABC dash. So what this does is we don't have to move our spindle to some other location and overwrite data. Overwriting data causes issues. We don't ever want to overwrite on the disk because of data integrity issues, and we want to maintain atomicity at all points. So it makes more sense to just have the update operation as a separate write entry. So when you have an update operation, make a new entry in the write-ahead log. You'll obviously update it in the hash map. You can just overwrite it simply over here. And periodically, you will flush the write-ahead log entries onto the disk, and the disk will also have the ABC dash, the updated entry of ABC. Now, of course, if you update multiple times, you can have duplications involved. One implementation, one solution for this is from time to time, maybe every hour or maybe every day, you can perform compaction of your database. So you can parse through this file and basically compact it, remove older versions of the data and replace it with the updated versions. If there's any data that is deleted, you can just scrap that off as well. Deletions will also be another operation. You can have OP delete and have that over here as well. And you can insert it into the database. And if you have a delete operation, you will be obviously removing that particular entry from your hash map. Now, I don't know about you, but I certainly had this question when studying this topic. And it's that, why do we have the hash index in memory to begin with? We know that the RAM is pretty constrained in its size and in its support for the key set. We'll have to have a very limited key set size to be on the RAM. And we also know that the time complexity for reads and writes is constant. So why not just push your index onto the disk? So the first point is, while the asymptotic time complexity is constant, and that's pretty great, but that's on paper. We use indexing for practical purposes. We're more concerned about the runtime, the real life practical implications of it. So while the asymptotic time complexity is constant, the runtime is very terrible on the disk. So if you recall from the initial slides, the average disk seek time on an HDD is in the order of milliseconds, 10 to the power minus 3, while for the RAM, seeking a block is going to be in the order of nanoseconds. So a RAM is 1,000,000 times better than an HDD. If you use an SSD, seeks is in the order of microseconds, but still a RAM is still going to be 1,000 times better than the SSD disk. The second point is your hash buckets might obviously have a value already in place. And in that case, you have to find out a new bucket. That new bucket is going to be some other block. So in case of collisions, you have to touch multiple different blocks. So you first have to go to the block or blocks containing your index, bring that onto the RAM, apply your hash function, see what block it maps to. If that block already has some node, tough luck. Let's say you go with the linear chaining method for collision resolution. Then you have to go to that node, see what the next pointer points to. It points to some disk address on the disk. Now go to that address on the disk, fetch that block, and if that also points to some other node, you'll have to keep accessing the disk. And obviously, that's not ideal. The third point is the most important, I feel, and it's about the property of the hash function. So your hash function's main goal is to scatter the points across buckets as evenly as possible. So let's say you get sequential data in order. You get ABC, then BCD, then CDE, then DEF. Even if you get this data in order, your hash function, when it computes the bucket for ABC, might map it to B1, block B1. But when it computes the bucket for BCD, the next item, the bucket won't be B1, it'll be B10. And for the third item, it won't be B1 or B10, it might be B3. And for the fourth item, it could be B1. So the scattering property of the hash function, even for sequential data, means if you're going to access data sequentially, each of those data points maps to some different block. So you're not making use of the property of locality of reference. A large portion of your runtime goes into fetching these individual blocks for these individual points. And that obviously won't scale well. So at the start, I mentioned that we can have two implementations of this hash indexing. We can have our entire record, which is stored in memory in the RAM, or the records can be stored on the disk and we can have a pointer to them, and that pointer will be in the hash map. Redis, which is an in-memory key value store, one of its primary use cases is for caching. Because it's used for caching, it has to serve a read request super fast. So it makes more sense for Redis to store the entire data in the hash map itself. All the records will be in the map. So you won't have a pointer on the disk. If you get a read request, you won't have to fetch blocks from the disk and service it. You can instantly retrieve it from memory. So back to your custom database application. You make all these observations and you are pretty satisfied with the results. First of all, you have this hash map which is in memory. It can service incoming read requests pretty efficiently. Your write requests are also taken care of. You have persistence with the help of this write head log, and you batch requests and flush them to the disk periodically. And even this process is pretty optimal. So what is the downside? When you think critically, one glaring downside is this right here. A critical functionality of any database is to service read requests very efficiently. Read requests make up the bulk of the operations for most applications. So servicing them in a very low latency fashion is critical. So it makes sense to have this hash map in memory and service your read requests instantly. Now, in order to do that, the entire key set should fit into the hash map. So that brings us into the first downside of using hash-based indexing. If the range of a key set is too vast to fit in memory, hash-based indexing probably won't be an optimal approach. Another downside to using hash-based indexing is the lack of support for range-based querying. So let's say you get this query, select star from employees where the name is in a certain range between A and X. Now it is infeasible to generate a list of all the possible names between A and X, compute the hash of them, and check if that value exists in the hash map or not. What you will be doing instead is doing a linear scan of your database, which defeats the purpose of having an index to begin with. So if your use case does not include a range-based querying, and if you're dealing with a small section of data, your data set is not too vast, only then is hash-based indexing a good approach. So let's say that your database actually does need to support large dataset sizes and also needs to support range-based querying. Then in that case, you might consider B plus tree indexing. So what is a B plus tree? It's a self-balancing tree It can be of any order. It can be 2 order, 3 order, 4 order. The image that I drew over here is a 2 order binary, is a 2 order B plus tree, excuse me. A 2 order B plus tree, each node will have at max 2 children. If it's 3 order, each node will have at max 3 children. So if it's 3 order, your structure might look something like this. You'll have at max 3 children, and the node itself will have at max 2 keys. So you can have one key over here, let's say this is 2, and the other key over here, let's say it's 7. So here you'll have values less than 2, values between 2 and 7, and values greater than 7 over here. So if it's an n order binary tree, each node will have n minus 1 keys, and the children will be at max n. So a B plus tree is a self-balancing tree which is kept entirely on disk for the most part. If your application just wants to support range-based querying and your dataset is pretty small, you can store it on your RAM in memory. But for the most part, it's stored on the disk. Because it's stored on the disk, there's no key set size constraints, and also persistence is a default. It's stored on the disk, but you'll still need a write-ahead log. And why is that? Let's say you have an update operation and you need to update this particular node that's shaded in red, and you do a partial update and then the system turns off. So you've essentially corrupted your data. So it makes sense to have a write-ahead log. Another approach to do it is, rather than overwriting your node, you can create a copy of that node, make whatever modifications you want to that node, to that copy. And once that node is done, you can just update the link to point to that copy node. And again, because this is a balanced tree, the average read-write time complexity will be logarithmic of n based the order of the tree. So while the write time complexity is log n, when you talk in terms of runtime complexity, there will be a write penalty, because number one, you're obviously writing into the disk. That takes time. And number two, you have this phenomena of page splitting. So let's take a quick example for a 3-order B plus tree. Step 1, you start with one node and you plug in 7, and then you plug in 2. And step 3, you want to add in 4, but you can only fit 2 keys at max. So what you do is you push 4 up top to another node, and to its left, you'll have nodes smaller than it, and to its right, you'll have nodes greater than it. And also, when you push the node up top, you will maintain a copy of that node as the leaf child. So all your leaf nodes will have all the keys which are present in your data set, and the leaf nodes will have the actual data. Then you want to insert 3. 3 can fit in right over here with 2. And then in the next step, you try to insert 5. So 5 belongs here, but there's no space. So you want to push 5 up top. Now, before pushing 5 up top, you also want to maintain a copy of 5 in the leaf node, because all the leaf nodes will contain all the keys of your data set. So that's what you do over here. 5 will have its copy over here with 7. 4 and 5 are pushed up top. 2 and 3 to its extreme left, and between 4 and 5 you have 4 over here. So obviously this entire write operation interacted with multiple blocks. This block here, this block here, this block was newly created and also interacted with this block. So there's a big runtime, write runtime penalty. I've also shaded this portion over here for this block containing 4, because while there's space for another key over here, 4 sits here all alone. So basically, while there is space, you're not utilizing that space. That concept is called fragmentation. So page splitting results in fragmentation. This, for the most part, won't be an issue because space, especially in the disk, is not that precious. So each node of your B plus tree could be thought of as one individual data block, which is on average 4 kilobytes. So this is neither too big nor too small. If it were too small, that means, let's say you can fit only one key in a node, the height of the tree will increase, so your log n factor goes up. Nor is it too big. It doesn't fit in 100 keys. If it fits in 100 keys, then that's no better than just doing a linear scan over your table. So 4 kilobytes is an appropriate size to store in decent order for your B plus tree. This B plus tree is also efficient for range-based querying. You can locate an individual key in log_n time complexity because of how the structure is arranged. And let's say you want to find all keys from A to R. So you find out the lower and the upper bound in log_n time complexity, and then you navigate to A and do a linear scan from A all the way to the upper bound. This is possible because the last layer is arranged in the linked list fashion. So we can see that a B plus tree supports range-based querying and also supports large data sets, which were not possible in a hash indexing approach. Now, for a layman, an index is solely a separate data structure for fast retrieval of data. So we have this one entity called the index, and on the other side, we have another entity, which is our database. We have our table file that looks like this. We have our records over here, and we have this separate structure called the index, which quickly references it. But the index can also double as a database by itself. So this entity, the index, along with supporting fast retrieval, is a database by itself. That index is called a clustered index. So let's say that your use case is to create an employee database, and you know that you're going to get a lot of read requests, and almost all of those read requests are going to be queried on the basis of the employee name. So what you do is, before inserting any record in your database, you will specify that the primary key of the database is the employee name, and you're also going to create a clustered index, and the cluster key is going to be the name. So then your database takes incoming write requests and creates a B plus tree in this fashion. So your clustered index is basically the database itself. And obviously, because your database is arranged in some fashion on the basis of this name, it's sorted on the basis of the name, you can have at most one clustered index for any table. So the leaf nodes over here, A, E, or X, along with storing the key, will also hold the entire record value. Now let's say 20% of your read requests are also on the basis of the employee age. In that case, what you can do is create a secondary index. A secondary index is again going to be a B plus tree, but over here you'll have the leaf nodes which have all the ages, but where is the value of the record? The value of the record will actually be a pointer, and it's pointing to this clustered index. So your secondary index's leaves won't have the record. They'll just have a pointer to the actual record. And where is the actual record stored? The actual record will be stored on the clustered index. Your clustered index is basically the database. So I think that's about it for B plus trees. To sum up, B plus trees, use it if you have a large data set, which is for most applications, and if you also want to support range-based querying. The average read and write time complexities is slower than that of a hash map approach. It's logarithmic n, and a added drawback is writes will actually deal with writing to disk blocks, and you can have a lot of page splitting, which can also cause fragmentation based issues. So in comes the last indexing technique that we'll discuss, which is LSM trees. So an LSM tree indexing approach consists of two components. One is a tree and another is a set. So LSM stands for log structured merge tree. So there is a tree, you're doing some merge operations, and you also have some log structure. So this tree is going to be your balanced tree of any order. And you also call this tree a mem table because it's stored in memory. The log structure is called an SS table, a sorted set table, and this is going to be immutable in nature and will be on the disk. So let's go into the application. So forget the SS table existed for a second, and let's assume you have created this particular index based on the incoming write requests that you've received. So you've created A, E, or X records with the appropriate value, and you've also maintained a persistence backup of it on the write ahead log. Now, one of the major points why we ditched hash indexing was that the amount of data that we can fit in the memory is quite constrained. So it makes no sense to just have this tree in memory and call it quits. So what we can do is we can define some threshold size for our tree. Let's say it hits t nodes. After it hits t nodes, what we'll do is flush all the data that we have in memory onto the disk in the form of this SS table. And so our tree will be wiped clean. Whatever data we had will be flushed onto the disk in the form of these SS tables. So the next time a read request comes in, let's say for RS10, you don't have anything in memory. You've cleaned the slate. So your read request will obviously have to go onto the disk. Now, you might think that will be linear time complexity, but that won't be the case. Because mind you, this is going to be like a binary search tree. The tree will be in a sorted fashion. So if you do an in-order traversal of the tree, you're going to get data in a sorted list. So when you flush data onto the SS table, which is on the disk, you will do an in-order traversal and flush it. So your sorted set is literally sorted. So the next time you have a read request that comes in, you just have to do a binary search on the sorted set. So let's say you flush in all your data from your memory table onto the SS table. And now you start receiving more write requests. So you write in a new value of A, you write in a new record B, C, and D. So the next time you get a read request for A, you will first look at your memory table and you'll get to this node and you'll return its value because this is the latest version of A. Let's say you get a write request for X, but X is not in this tree. So what are you going to do? You're then going to go to the disk and you'll read from each of your SS tables. So you look at your SS table 1, you'll do a binary search over here and you locate X and you'll retrieve that. Now, it could be the case that you've again hit the threshold limit in your memory table, and now you need to again flush all the contents onto the SS table. You won't touch this existing SS table which is created because recall the SS table is going to be immutable in nature. So what you'll do is you'll create another SS table, do an in-order traversal of your memory table and flush all that content over here. Now, when you get another read request for A, let's assume your memory table is blank. You've recently flushed contents onto SS2 and you get a read request for A. So you'll first query the most recent SS table and see if A exists over here. If it does exist, you'll return its value. Let's say you get a read request for B. B does not exist over here. You've done a binary search here, so you'll move on to the next recent SS table, and check what B's value is over here. Now let's assume that the threshold limit is going to be t nodes. So once your mem table, your tree, has more than t nodes, you're going to flush the content onto the SS table. Let's also assume that you have n nodes in total. So this includes all the entries in your SS tables plus the nodes in your tree. So at max, how many SS tables do you think you're going to have? You're going to have n over t SS tables. And if a new read request comes in, you're going to do a binary search on each SS table. And we know that an SS table at max will have t entries because that's what you're flushing from the mem to the SS table. So it'll be n over t log t, the time complexity for a read operation. Now we know that for most real life applications, the threshold limit is going to be very minuscule compared to n. So this right here, we can upper bound it. It's going to be less than equal to upper bounded by having t upper bounded by n. So in that case, it's going to be upper bounded by log n. So the upper bounded average time complexity for read is again going to be log n. Now what about writes or updates? Any write that comes in, any update that comes in, you just push it onto this node. You don't have to deal with page splitting over here because this tree is in memory. So you can just create a new node, and if need be, you can shift nodes around to have self-balancing. So in conclusion, the read time is going to be log n and the write time is also going to be log n. But if you look at the runtime complexity for write, it's very optimized because you don't have to deal with the disk. Now you might think that your read requests over here are going to be pretty inefficient compared to B plus trees because you also have these multiple SS tables to worry about in addition to your memory table. But we can have optimizations around this. So let's say you have SS1 and SS2 and there's a lot of duplications involved. You can have multiple updates. Let's also say that you have SS3 over here, and in SS3 you're trying to delete B. So we can say B has been deleted. We can add a tombstone marker for B. So periodically what we can do is we can perform compaction of our SS tables. Mind you, we don't edit anything in any SS table. SS tables themselves are immutable. So when you perform compaction, you're creating a brand new SS table. So what compaction does is basically perform linear merge across all your SS tables. So between SS1 and SS2, you know that you're going to factor in AS20 because that is the latest version, and you'll write it over here. You'll then take BS12 and you'll then take CS4 with RS9. This is one temporary copy that you've done. You'll then perform the compaction between this and SS3, and that will result in AS20. You know that B has been marked with a tombstone value, so you won't consider that. You'll have CS4 and you'll have RS9. So this is going to be the latest version of the SS table, and you'll only consider this and you can discard the others. So in the worst end, the read time complexity is going to be log n, but we have the added benefit that reads are also undertaken by the in-memory structure, your tree. Writes are also going to be very efficient. For writes, we don't have to touch the disk at all. We can just push the entry onto the in-memory table. Of course, we eventually flush the contents onto the SS table, but that is done periodically, batch-wise, and it's an efficient process. Let's do a quick summary of the three indexing approaches that we've seen so far. Starting off with hash indexing. The pro is constant time reads and writes, which is in memory, and the cons is the entire key set should fit in memory and obviously no support for range queries. We then went on to B-tree indexing, which solved these two issues. It supports range querying, and because the entire structure is on the disk, there is no constraint on the key set size. The cons over here is because the reads and the writes both have to go to the disk, there is slow writes to B-tree because the structure is on the disk. Lastly, let's talk about LSM trees. The pros are all the pros of B-trees. It supports range queries and there's no constraint on key set size. And there's also very fast writes to memory. This can be seen as a sort of a con. The reads over here, when you talk of the runtime complexity, not the asymptotic time complexity, the runtime complexity is slightly slower because in the worst case, you have to do a login query in your in-memory table plus a login query for each of your SS tables. So runtime wise, it's slightly slower. Another con is you have a lot of background tasks to perform. One of them is compaction of your SS tables, flushing content from your memory to your SS tables. So that requires extra CPU computation. So if you deal with data on scale, it makes sense to choose either a B tree or an LSM tree. If the overwhelming majority of your requests are read requests, it makes sense to go with a B tree approach because the runtime complexity is going to be pretty quicker compared to an LSM tree. But if you have a healthy mix of read and write requests, or write requests too are not an insignificant factor of your overall requests, we can go with an LSM tree based approach. Let's now talk about two unconventional yet very widely used indexing applications. One is for search indexing and the second is geospatial indexing. Let's understand search indexing with the help of this use case. So you're on Amazon's website and you type an apple in the input text. You actually want the fruit and not the computer. Now let this red box be Amazon's backend. It has these records where the primary key is the document ID and it maps the product that it serves. So Amazon takes in your input apple and in a naive sense goes over this database, this data linearly, and for each document ID looks at each term and sees wherever apple is there, and filters these 5 records into 3 records with Apple Computer, Red Apple, and Green Apple, shows it to you, and you can select whichever apple you're actually interested in. Now, obviously, the point of indexing is to have fast retrievals. So you might think that rather than scanning linearly, let's introduce an index, maybe an LSM tree or a B tree. Now, when you create an index out of these terms, it'll be in a sorted order. Now, you want Apple, but you won't exactly know always what the actual product name is. In this case, we don't have anything called a normal apple in our listing. We have green apples or red apples, and also the Apple Computer. So you might erroneously return Apple Computer, or let's say you wanted computer. You wanted computer to begin with as your search term, but you don't have computer anywhere here. So your indexing is totally useless. So we need to go with another form of indexing specific to searching for prefix or suffix, or better yet, substrings. So search indexing, the primary use case is for text searching. Given a search term, how do we query it against a bunch of text terms, keeping in mind that the search term given to us is not complete. It could be a prefix, it could be a suffix, or it could be a substring of the string. So traditional indexing methods won't work here. So we go with search indexes. Now search indexes are inverted indexes. So with traditional indexing, we map the value to the key. So we associate the key with a value. But in search indexing, we flip it around. We associate the value with the primary key, with the document ID. So what we do is, given Amazon's catalog, the bunch of documents with the products that it serves, what we do is we parse through this catalog and look at each document and tokenize it. So create tokens out of each term. So in this case, if you have capital APPLE, when you create the token, you might strip it off all the apostrophes, all the capitalizations, you will lowercase it, APPLE, and you will store this in your index along with the document ID as the value. Now, Apple belongs in multiple different document IDs, so the value will be the list of documents that it is contained in. So you'll effectively create this particular search index. And now when you receive Apple query, you can instantly go to Apple in login time complexity, assuming you have implemented this using a B tree or a B plus tree, and look at the documents that it is in and retrieve that. What you most commonly would be using is not a B plus tree, but rather a trie data structure. So trie looks something like this. So let's say you search for Apple. So it looks at APPLE, and towards the end, the word ends for Apple, that term, and you can retrieve that particular record. If you search for, let's say, ape, it looks at this branch instead. So I won't go into the details of a trie data structure, but most likely for search indexing, for search terms, you'll be using a trie structure. If you use a B plus tree, the time complexity is going to be log n. For a trie, it's going to be the length of the term that you're searching for. Now, let's say this is our catalog, Apple, Blueberry, and Blackberry with the document IDs. And this is the search index that we've created. We flipped it around. Now, if I'm given Apple, it's pretty easy to search where Apple is. You just look at the prefix. So whatever we have done so far, converting this to this helps in prefix searching. But what if I have this as the catalog and I'm searching for a berry? In this case, I don't have any term that starts with berry. Berry is in the suffix. So how will I have suffix searching here? So what I will be doing to implement suffix searching is, when I create the tokens, I will also flip those tokens around. So APPLE gets flipped to ELLPA, and I maintain a second inverted index. This is the first one and this is the second one. So when I'm given the search term berry, I'll first look at the prefix. Does it match any prefix? If it does, filter that. And I'll also look at this particular index over here, the flipped tokens. I'll flip the query. I'll get YRREB, and I'll be looking at this flipped inverted index and see that there are 2 records matching with this. That means the suffix matches, and I'll return those 2 records. So in conclusion, search indexes take in a typical document and they tokenize each term of the text. They map it to the document ID. It essentially creates an inverted index. And along with doing prefix searching and suffix searching, you can also do substring searching, or you can also do fuzzy searching. All that's implemented by a very popular open source library called Apache Lucene. So I'm not going to go into Apache Lucene's details, but some few high-level points. It started in the late 1990s and it is the most popular open source search index, and it supports many different types of indexing for complicated variants of search. So apart from just basic prefix and suffix searching, it also finds words that are closer to the words typed. If you have a typo in the term, it'll still figure out what you're trying to search for. It implements geospatial searching, which we'll look at in the next section. Proximity searching, basically finding out restaurants near you, finding out Uber drivers near you. The most important bit about Apache Lucene is that it's typically meant to be used for a single node. But for most modern day applications that are distributed in nature, you want your search index to also span across several nodes. So for that, you'll be using another library that's just a wrapper on top of Apache Lucene, and that library is called Elasticsearch. Let's have a quick high-level overview of what Elasticsearch is. So Elasticsearch is basically just a wrapper library around Apache Lucene to basically implement search indexing in a multi-node distributed setup. So Apache Lucene's main intention is to be used in a single node setup. If you want to scale it across nodes in a distributed environment, you will have to individually deploy the Apache Lucene instances across the different nodes, handle partitioning, handle load balancing across these nodes, and also handle a replication all by yourself. But if you were to use Elasticsearch, all that is managed. It manages the replication and partitioning. So you just have to provide configuration details about the nodes in your environment, and the Elasticsearch process takes care of replication and partitioning. Let's take a look at the third point for Elasticsearch, and it's that it maintains a local index per node, which leads to less duplication. So what does this mean? So let's first take a look at what global indexing is and then move on to local indexing, which is what Elasticsearch implements. So in global indexing, you'll have multiple partitions, multiple shards, and globally, you'll have a bunch of search terms. In this case, globally, you have three search terms: apple, banana, and cherry. Now, these search terms are obviously going to be associated with some document ID or a list of document IDs in this case. This is an inverted index. That's how search indexing works. Now, most likely, you normally don't just associate the document ID as the value. You'll most likely associate the entire document text, the entire document basically, with the search term. For example, going back to the Amazon case, you will associate with the MacBook computer search term text. To it, the value will be the entire document value. The document will have some ID 25, and the value will be all the product details for this particular product, the images that it contains, the internals, the specifications, all that will be part of the document. So in global indexing, for each search term will strictly be confined to one shard. So globally over here, you can see that you have three search terms: apple, banana, and cherry. Think of it like our entire product catalog has just three things: apple, banana, and cherry. So if you have two shards, Apple will strictly be confined to one shard. So Apple and all the documents that it belongs to, you will maintain that map only on one shard. You won't have Apple with document 23 here and Apple with document 26 over here. Similarly, for banana, the single banana instance will reside on this particular shard. On any other shard, you won't find banana mapped to some other document. All the mappings for banana is confined to this particular shard. So what is the downside to this? So as I said, the value won't just be these document ID numbers 6, 10. For most practical purposes, it'll be the entire document, the entire product description with the images and so on. So Over here, taking the example of Apple and the documents that it contains, that it's contained in is 23 and 26. But if you look over here, Cherry is also contained in document 6 and 23. So what are you doing over here? In this shard, you're plugging in the entire value of document 23 and Apple is referencing this. And in this particular shard, you're again plugging in the entire value of document 23 and Cherry is referencing this as the key. So this obviously won't scale well. You'll have a lot of data duplication. You're also dealing with replication over here. So a lot of documents will keep on flying across these different nodes. So that's a lot of overhead in our network. So what Elasticsearch actually does is it instead goes for local indexing. So in local indexing, what local indexing entails is we have these multiple shards and we assign documents specific to one shard itself. So in this case, 23 and 26 documents are solely going to reside on shard 1 and 6, 10 and 25 documents, the entire document value, will solely reside on shard 2. So you assign the documents to a specific shard and now this node will construct the inverted index out of all the search terms, out of all the tokens that are present in these documents. So in this case, 23 and 26 are in this particular shard, and you know that Apple and Cherry belong to those documents. So you'll construct this particular inverted index. Same way with banana and cherry over here. So in this case, you don't have any duplication of data. You don't have to send document 23 or 26 or 6 or 10 across the network. But the downside for this is if you get a query for Apple, at least in global indexing, you know that Apple will solely reside on this particular node and you will instantly have access to all the documents that Apple is contained in. But in the case of local indexing, you'll have to individually query each particular shard to know where Apple is, and also you have to fetch those documents. So query retrieval over here, you'll have to touch each shard. So ideally what we like to do is to confine all our searches to a single node. So let's take the case of Amazon Fresh, which is mostly for groceries. So you can have all your documents, all your grocery catalog, and build a search, an inverted index, a search index on this particular shard. So when you go to Amazon Fresh, which is a different endpoint, all your search queries will be directed to this particular node. But if you go to the normal Amazon website and you type Apple, it could mean anything. It could mean a fruit, it could be the electronic device, it could be furniture, it could be anything. So in that case, you can't specifically direct it to a node. You don't have a node built for that particular context. So in this case, you have to distribute your search, your query across the shards. Let's end this video with a short segment on another use case for indexing, which is geospatial indexing. Geospatial indexing is used for proximity searching problems like finding Uber drivers near you or finding restaurants near you. So take this 2D Cartesian plane as a reference, and these coordinates over here are positions of restaurants. It's a static picture of the restaurants, and you are right here at point 22. Now you want to query all restaurants that are near you. So one way to do this is to do a linear scan of all the data points in your restaurant database and find out which ones are closest to you. But that is a linear time complexity operation. You also know that having an index would speeden up read queries and make them more performant. So what you decide to do is create an index on the basis of the x coordinate. So you do that, and the logical view of the index would look something like this, where the coordinates are sorted on the basis of the x coordinate. Now you filter it based on these two records because of the x coordinate. Your x coordinates are pretty close to you. You are at 2, 2, and this is at 2 minus 4, and this is at 2 minus 1. So that'll give you these two restaurants over here. But looking ahead from a macro picture, you know that these are clearly not the closest ones. The closest one is over here, which was not picked up by our index. So then you decide maybe to index it on the basis of the y coordinate. So if you decide to do that, it'll give you all these restaurants over here where the y coordinate is 2. But this again misses this particular restaurant right here. So maybe you then decide to not have an index just on one coordinate, but on two coordinates. So you create a composite index. So we've looked at three indexing terms so far. One is clustered indexing, if you recall. The second one is secondary indexes. All the other indexes, apart from your clustered index, is a secondary index. And the third form of index is a composite index, which is composed of multiple keys. So in this case, it'll be composed of the x and y coordinate. So when you create a composite index of the x and y coordinate, it'll be sorted on the basis of the x coordinate first. And in case the x coordinates match, you will then sort it on the basis of the y coordinate. So let's say you create a composite index and then you apply this particular query. Select all points where x is within a certain range, let's say between 1 mile, and you filter it to this range. So this will give you that x range. Now again, this x range will have a lot of points within it. So now you also have to filter it within the y coordinate range as well. So let's say you are over here, but there's a problem. This right here is arranged in the form of x and y coordinates. It's sorted in the base of x, and if there is a tie, it'll be sorted on the base of the y coordinate. Let's say you decide to filter based on the first part of your query, x minus r and x plus r, to just these records right here, 5.1 till 5.2. Now the problem is the y coordinate section is not sorted. So what you can do is take this out and now sort it in the base of the y coordinate as well. So that'll be an n log n operation. A better approach is to, once you filter it on the base of the x coordinate, do a linear scan on this filtered record and analyze the y coordinate and check if it matches your criteria as well or not. So let's say 8 is too far as a y coordinate, so discard that. 10 is also too far, and then you just consider these three records. Now again, this is a linear operation in the worst case. So the point I'm trying to make over here is that for proximity searching problems, relying on one coordinate or two coordinates or relying on the coordinate itself as a metric does not make much sense, and it's inefficient. So the basic idea behind geohashing is that you take a 2D coordinate xy and you compress it to a single string, which is called the geohash. So let's take the example of this solitary point over here. And this is the entire Cartesian plane that you have. Now, the end goal is to have this particular point confined to a box which is of a certain size. So let's say the point will be narrowed down to a box which is at most 1 square mile. So this entire region is 1 square mile. So we'll keep segmenting our boxes into even smaller boxes and ultimately confine this point to a smaller box whose area is 1 square mile. So we start off with segmenting our 4 areas into A, B, C, D. Now we know that our point is within this region C, and the area is way more than 1 square mile. So now we further segment it into 4 areas, CA, CB, CC, and CD. If you look at this region now, the second quadrant, the area is still more than 1 square mile. So you decide to further segment it into CBA, CBB, CBC, and CBD. Ultimately, you find that CBA is a square mile and you're satisfied with the resolution of the particular point. So the fully qualified name of this particular point is CBA, and it's enclosed within CBA, which is inside CB, which is inside C. So if you can take a look at the full name of this point, the prefix are C, CB, and CBA. So the increasing order of the prefix narrows down the location of the particular point. So let's say tomorrow you were tasked with finding out all those points which were closest to this particular point. So obviously you will start off with considering only points within this C quadrant. So just these points. You'll further narrow down your search by considering all points within this CB quadrant, which is right over here, and keep narrowing down until you hit a desired resolution. So let's take another example. You have your point over here. This is your location, and you have neighboring points around you, and you've segmented this particular Cartesian plane into multiple segments, and you've assigned a particular geohash for each of these points. So this is the geohash that you've constructed for each of these points, and you've created this and maintained this in a B or B plus tree. So basically all the points are in a sorted order based on the geohash as the key. So BAB will point to some XY coordinate, BAC will point to some XY coordinate, And of course, you can have multiple points which have the same geohash. They'll be in the same box, but their coordinates will be different, x, y, and x dash, y dash. Now, depending on the precision, which is BC, which is more precise, and BCB, the region that you're talking about is different. The size of the region that you're talking about is different. So B over here, the context is a much bigger region. And at least for this example, we've taken that to be 4 miles. If you further chunk B into 4 equal segments, then BC will be 2 square miles, which is this region right here. And if you further segment it equally into 4 segments, this region will be 1 square mile. Now, your task is basically to find out all points which are 1 square mile apart from you. Not 1 square mile, 1 mile apart from you. So if you're over here, within this particular radius, gather all those points which are within a mile radius away from you. So how do you go about doing that? So the first step is identifying the geohash for your coordinate, what box you're in. So you know that A is some range in terms of x and y coordinate, and you know that your x coordinate is greater than A, nowhere near it. So you discard this box, you discard this box, and this box. Now you know that B also is segmented further down into BA, BB, BC, and BD. So you see that BA is within a certain range in terms of x and y coordinates. So you decide to skip that. Same way with B, same way with D. And you focus on the BC part. You keep narrowing it down based on the geohashes that you have defined. So the most precise geohash that we will find is 3 letters long. So once you hit 3 characters long, you're going to stop right there and you've identified the geohash for your coordinate. Next, you're going to look at all your neighbor boxes. So in this case, you have 8 neighbor boxes. For all these 8 neighbor boxes, you're going to find out all the coordinates that belong to these 8 neighbor boxes. And how are you going to do that? With the help of this index that you've created over here. So it'll be a log n time complexity to find out all those coordinates which are residing 8 directions around you. Once you've got all those points, you can go over all those points and figure out the Euclidean distance between them and you, and filter those points and consider only those which are a mile apart from you. So let's end this video with a quick note on geosharding. So let's say this Cartesian plane represents the US and the top right is the New York region. New York City, New Jersey, surrounding cities. So you know that these cities are very densely populated. You have millions of data points over here. So the precision between the points over here can span multiple letters. Compared to other regions of the US, the Midwest and surrounding areas, the data points won't be as large. So you can make do with a pretty large bounding box and less precision for each of these points. Also, because you have millions of entries over here, all these entries can't possibly fit in just one node. It makes sense to distribute these points across multiple partitions. So for the New York region, for the top right, we can have 4 nodes, 4 partitions that deals with each of these regions here. While for the other states, for the other regions, we can just have one big node for this, one big node for this, and for this. Or we can just have one computer that deals with these 3 regions, which has a relatively lesser sparse data points. Let's talk about ACID transactions in the next video.